Guys, welcome to this video. So in this video I want to talk about uh, how not to hate physics part 2. So I released a video titled how not to hate physics back in I guess around 1 year back or something. I was recently rewatching that my old video, and I was like probably I felt like I didn't do a very good job about I made my points clear. I gave a lot of good illustrations about why physics is a subject that is enjoyable, that can be enjoyable if we approach it the right way, of course. And that is a very beautiful subject. I mean, beyond being just an important subject or just a fundamental subject, it can also be a beautiful subject. And that's why at least we should not hate physics. That's what I wanted to convey in that video, how not to hate physics. So in this video I will share some more unusual illustrations, and I will try to bridge the gap between our everyday life, which every one of us is familiar with regardless of whether or not we study physics. So we'll try to bridge the gap between that, our everyday life, our day-to-day experience, and physics. I'll try to draw analogies and stuff, and give you some unusual but I guess interesting and beautiful illustrations. So it's kind of a how not to hate physics part 2, and I think you'll like the video. I'll try my best, of course. So the first thing, you see, recently I was discussing with one of my professors at my college, and also with one of my friends, and I was just thinking about this myself. Whenever so physics is the study of the world around us, right? I mean, just a very basic definition of physics. This is when you introduce physics to high school students. What do you say? What is physics? Why do we even study physics? It's just the study of the world around us. I mean, that's what science tries to do. Even biology is a study of the living creatures around us. But physics wants to, I mean, at least conventionally, physics wants to break things up and go to the root, go to the heart of it all. What is everything made of, and that kind of thing. What did everything come from, and all this stuff. But see, whenever we are talking about the world around us, the first thing that strikes us, I mean, that strikes a lot of us. I mean, one of the things that is easily noticeable about the world around us is that nothing is constant. Everything is changing. It's dynamic. The real world around us, it's dynamic. It's changing, and it's so complicated. So whether you're talking about the evolution of whether you're talking about long-term changes like the evolution of the universe, the formation of structures in the universe, or the evolution of the animals and of the living creatures on earth, or whether you're talking about short-term changes like maybe a small quantum fluctuation in the vacuum, or let's not get to that level yet, something we can observe like the clock ticking, or maybe the wind blowing and this kind of thing, but it's all changing, right? Now, the first thing is that whenever we're doing science or whenever we're doing physics, I mean, that the basic philosophy that is guiding us is we try to look for similarities between different phenomena. Like, for instance, uh, to use a very common example, an apple falling down and the moon, which is just a kind of back then, it was when there were before Newton and all, people were like, okay, that's just something which just hangs in the sky. So apparently they are different phenomena, moon and just an apple falling down. But it took a physicist like Newton, or I mean, it took a physicist to actually show us that they are actually similar. Both the motion of the moon, of course, we cannot. The moon appears to be just hanging in the sky, but actually it's moving around the Earth, and all of these observations and all. But both the motion of the moon around the Earth and the motion of an apple falling towards the Earth, both of these apparently different phenomena, both of them are governed by the same law, that is the law of gravitation. So then, for instance, an example which I use very commonly whenever I'm explaining this stuff to maybe to my juniors in college or to my friends or whatever in my YouTube videos. Also, I guess I've used this example many times before in my previous videos, YouTube videos. Water, because this is a very good example. At least I find it to be a very good example. Ice, water, and water vapor. They are like apparently they're very vastly different substances. One is solid, one is liquid, one is gas. But then on further study, we found out that they're all composed of the same kind of molecules, two hydrogen and one oxygen. That is the H2O molecule, and they're the same molecule, two hydrogen and one oxygen arranged in the same way in all these three: water, ice, and water vapor. But the arrangement of the molecules, they are different, and this is what gives rise to the difference. For instance, in ice, it's like the water molecules are arranged in a particular pattern, particular structure. In water they're more loosely arranged in a different way, and in gas they're even more loosely arranged. So that is what is giving rise to this difference, but ultimately they're made of the same thing. So in a way we have, at least chemically, we have established the similarity between these three apparently different substances, and we've also, and once we've identified that they are all made of H2O molecules, then we can further study the phenomena of, like, these phase transitions between solid and liquid. What happens when, for instance, ice is melting, or, I mean, for instance, water is condensing to ice, and all that stuff. And what I love about physics is that, and that is what I want to convey in this video to you, to whoever you are. I don't care whether you are a physics student or you don't have any technical knowledge in physics, or whether you do, because this is a very interesting point. Let us first of all talk about for instance, water melting into ice or something. So, for instance, or let's even talk about, yeah, let's talk about that. So, we start with water, which is a liquid, and then we are trying to. So, when water is melting into ice, or let's even start with gas, which is water vapor. So, water vapor or gas, it is symmetric. Now, when a physicist uses the term symmetry, usually in most of the cases what it means is that it's not it's not always, it need not be a geometrical symmetry, like for instance a spherical symmetry. That's important. Spherical symmetry is very important to physicists. We use that a lot, to like, for instance, if something, for instance, central force, it depends only on the radial direction, the r coordinate, not the theta and phi. But yeah, let's not make the discussion technical. But symmetry means gas is symmetric. When I say gas is symmetric, it means gas molecules are, pretty loosely arranged, and they're just flowing around, and they're in absence of any external force or anything, they're just uniformly distributed throughout the space. So it's kind of isotropic. I mean, if I'm standing here and there is gas molecules everywhere uniformly distributed, then in whichever direction I look, I will find the same amount of the same some gas molecules randomly moving around. The same thing. Like if I just look in this direction and take a snapshot of all the gas molecules, I'll get a particular, just a random, they're uniformly distributed. And if I just look in a different direction, I'll get the same thing. I mean, not the same molecules in exactly the same kind of arrangement, but overall it's the same thing physically. So that means I cannot distinguish the direction. If I'm surrounded by gas, whichever direction I look, just gas molecules, I cannot distinguish. That is what I mean by symmetry in this case, just to give a rough idea. But so yeah, gas is in a way symmetric. But water, well, water is symmetric in the sense water doesn't have any shape of its own, of course. But water is, the symmetry of water is a bit constrained. I mean, it's lower than the symmetry of gas. Why? If you just want try to understand this intuitively without going into the technicalities, because water will flow in a particular direction. So that means whenever water will always flow from, I mean, by itself, water is not as free to move as the gas molecules, of course. And of course water will take the shape of the container you put it in, and all those stuff. It will, I mean, it's easier to distinguish the, for instance, water, it's easier to distinguish the different not only the direction. It's not always about the spatial direction, but it's a lot of other stuff as well. And when we move to the level of ice, see, ice is even less symmetric, because by itself, when ice forms, I mean, when ice forms, I'm not talking about snowflakes or the ice cubes in the refrigerator, because we just put the water in those cube shaped stuff. That's a different thing. But when ice forms naturally, they just form in any random shape. I mean, for instance, ice can grow in that direction. So suppose in natural conditions, under natural conditions, when ice forms in very low temperatures, at very low temperatures, the ice can grow. It does not grow uniformly in all directions. It grows in a particular direction. There are a lot of reasons why, but in that sense, ice is less symmetric. It has the least symmetry between gas, water molecule, and ice. I mean, gas, water vapor or gas, and just liquid water and ice. Out of these three, ice has the least symmetry. So that is all about symmetry. Now let's talk about energy. Of course, gas has energetically, gas is much more energetic than water or than ice. Water is more energetic than ice, and gas is energetic than both of them. Gas is the most energetic, because the gas molecules, the gas particles, they are free to move about. That means they have energy. They have that. Gas is usually at high temperature, we have water vapor, and as we cool down, we get to water and then to ice. So in physics, we have, in classical physics, there's a direct correlation between temperature and energy. Half kBT. Kb is a constant, Boltzmann constant, and I mean, in gas molecules, see, as we're increasing the temperature, the molecules are vibrating, and that is what gives rise to the energy. And At very high temperatures, when there is the, I mean, when we have the gaseous phase of matter, gaseous state, then the molecules have usually very high energy. That's why they're free to move about. So ice has very less energy. The ice molecules, they are pretty, the ice is a solid, they are pretty constrained, they are not free to move about. So as we're just, I'm just trying to give you a rough idea, because this does not hold always, but to give a rough idea, as we are decreasing the energy, the symmetry is also breaking. Gas is perfectly symmetric and isotropic, and it has high energy. So symmetry exists, kind of roughly speaking, symmetry exists at high energies. If we decrease the energy, or in other words, if we decrease the temperature, cool down the system of gas, after a critical temperature, it becomes liquid. It condenses into liquid, and the symmetry breaks. I mean, the symmetry decreases by a good amount. And then do this further, and then we get ice. Right. So that is all about symmetry and energy. Now let's talk about entropy. So because see, I find like symmetry, energy, and entropy, or you can say EES or ESE or SEE. It's better to call it SEC, SEEC, symmetry, energy, entropy. So these C, or these three players, I find they are very important players in this game of the universe. Because whenever you're studying any complex system, it need not be water and ice, it could be anything for evolution of any complex systems, because these are fundamental players. And the fundamental laws of physics which govern these players, govern these parameters, they, at least we expect these laws to be universal. Universal means they apply to all systems, right? So let me just give you, before that example, before this example, let me just talk about, we talked about symmetry and energy in terms of water, ice and water vapor. Now let's talk about, in context of the same H2, this water, let's talk about entropy. So entropy, for those of you who don't know, entropy is basically, roughly speaking, it's a measure of disorder, which is the definition which most popular science books will give you. But to make it a bit more rigorous, because see, what I find is that it's always important to, popularizing science is very important, because only then, if you want to get people interested in science, for instance, if you want to get high school students, or maybe sixth grade or seventh grade students interested in science, then you cannot just always start with the technical equations and stuff. This popularizing science, or explaining science in simple terms without the technical rigor, is important. But I think it's equally important, if not more, to make sure that while we're popularizing science, or while trying to make science accessible to the general audience, we should not play with the rigor of the theories. We should not play with the intricate details and the mathematical rigor or the technical rigor of, because oftentimes what happens is that when we're trying to popularize science, we just to keep things simple, we oftentimes we give wrong ideas. I mean, we explain the wrong concept. Okay, so he's just a kid, so maybe we'll not understand the actual technical things. So just to make it simple, let me just give him a wrong concept. Making science simple is important, but it's also important to not tamper with the rigor. Because why I'm saying this, because it's difficult to unlearn wrong ideas than to learn new ideas from scratch. Suppose if someone from a young age is exposed to a wrong, incorrect concept, which, see, overall it looks okay, but actually if you go deep down, that concept is actually incorrect. Then at a later stage, if that person pursues science, he or she will find it difficult to unlearn that wrong idea. And so in that sense, it's better to just uh, yeah, better to just learn the technical details when we grow up from scratch, but not learn incorrect stuff just in the name of popular science. That's also important. So yeah, that's anyway, what I was saying is that entropy. So entropy, when I say entropy is measure of a disorder, I don't actually give it the full picture. Entropy is actually, roughly speaking, the number of ways you can achieve a particular configuration of a system. This definition is enough for our purposes in this video. I will not go into the other technical details. Actually, entropy is a very fundamental concept. It's not, although we first come to hear of entropy when we study thermodynamics, but it's actually much more. Thermodynamics is an empirical science, macroscopic science. Entropy actually stems from statistical mechanics, if we want to go to the roots, and it's a very important concept. All those Boltzmann hypotheses. There are a lot of players here. Like there is something called PEAP, which is the postulate of equal a priori probability. Then ergodic hypothesis, Liouville's theorem. I mean, all of these are not required for entropy, but yeah, this is all connected. And then you would have to define Boltzmann's entropy. That's KB ln W, or sometimes wherever it is ln P. Like what is the mathematical probability and what is the thermodynamic probability and all those stuff. But yeah, basically entropy is the number of ways you can achieve a particular configuration, particular arrangement. Just remember this for now. So now, keeping this in mind, from using this definition, can you tell me what, like, will the entropy of gas be more or will the entropy of solid be more? Entropy. I'm just talking about entropy. See, this is a very difficult. I mean, this is a very. It gets pretty confusing. But you see, of course, the entropy of a gas will be more because the energy. See, entropy means not just the physical arrangement. Like for instance, I give you 3 points and I give you three boxes, three balls and three boxes. So there are a lot of, and let's assume that they are not the same. They're not identical balls. They are differently colored. Like say one red ball, one green ball, and one blue ball, and three boxes. So there are many possible arrangements. Like for instance, you can put all the three balls in box one and keep box two and box three empty. That is a possible arrangement. You can put say the red ball in box one, the green ball in box two, and the blue ball in box three. That's a possible arrangement. You can put the green ball in box one, the blue ball in box two, and the red ball in box three. Since they're all, that's a different arrangement because I have numbered the boxes differently: box one, box two, box three, and the balls are also differently colored. So there are, you can see there are, if you just apply permutation and combination, there are a hugely many number of possible arrangements. But now if I give you just a single box and three balls, then there is only the number, then there is only, see, you have only one box. You don't have three boxes or more than one boxes. And you have to put all the balls. So there are how many possible arrangements? Either you have to put all the three balls in the same box. Or if it's allowed, then you can put just a single ball in the box or two balls. But in any case, the number of possible arrangements will be less than the first case when we have three balls and three boxes. So of course the entropy will be less. That is what I'm trying to say. Just an example. So in case of gas, it's since the gas molecules have more energy, so they more energy means they can move at higher velocities. If you have less energy, then there's a limit to the maximum velocity that you can attain, of course. So then that means they can move at higher velocities. That means they can move around the place. There are many different possible configurations. And configuration means not only position configuration, like this position in space, it's also velocity configuration. Like suppose the gas particles are moving around, and if I just take a snapshot at this particular moment, then snapshot means at this particular moment I measured just a thought experiment, not physical, of course, not in reality. I measured the position of each particle as well as the velocity of each particle. If I know the velocity, I technically know the momentum, energy, all of that. Then that is the total configuration. In the next moment, the position is changing, and as the velocity is also changing, because suppose two particles collide and this particle is moving in this direction, and after collision it is deflected in some other direction. So the velocity changes. Velocity means both the speed and the direction. So everything is changing. So of course a gas has more number of possible configurations and a higher entropy than say solid, because solid is of course the motion is limited, plus it's a solid than an ice, because usually solid means it should be crystalline. Crystalline means the arrangement should be a perfectly lattice arrangement, like those dots arranged like in a lattice, perfectly ordered arrangement. So a solid has very less entropy, right? We cannot measure the entropy actually. We just take a reference like zero entropy at zero temperature, 0 Kelvin, and then we just, but we only measure the change in entropy actually. Technically, physically we can measure the change in entropy. We cannot physically measure the entropy of a, but anyway, solid has very low entropy. Ideally zero entropy almost. In some cases that's what we assume, that solid has a perfect solid. For instance, glass. Glass is not a solid. Glass is technically a supercooled liquid. Of course, glass does not flow like water and other fluids, other common fluids, but glass is a liquid. It's actually a supercooled liquid because see, this is the beauty of whenever you're trying to, suppose we have some material, silica or something, whatever, and you cool it. So if you just vary that rate at which you're cooling, the rate at which you're decreasing the temperature, then you will get glass. Because for instance, if you cool the whatever you have, if you cool it very fast, cooling it means decreasing the temperature. That means taking away the energy of the particles in the system. So that means if you take away the energy, then before the particle can reach the perfectly stable crystalline arrangement of a solid, before that they have all the energy is taken away, so they cannot move any further. So in a glass the particles have not yet reached that perfectly solid crystalline arrangement, but still they have freezed, they have solidified. Solidified meaning you have taken away all the energy, so they cannot move any further. That means we get a kind of a frozen glass state. So it looks solid because of course glass cannot flow and anything, but it's actually a supercooled liquid, glass. And depending on you can get different kinds of glass depending on how fast or how slow you cool the system. So it's all depends on that. Ideally systems will always try to stay in the equilibrium state. the lowest energy state, solid. But if you just very fast, if you take away the energy, then before even they reach that state, they will just freeze, and that's what happens in glass. But yeah, glass of course has lower entropy than gas, but it's not the lowest entropy yet. I mean, it's kind of a, like you can say, false vacuum, or a false equilibrium. Like it's not it's a local minima. It has an equilibrium. Glass is, of course, glass is in equilibrium. Glass does not by itself break or anything, but it's not the lowest possible energy. It's not the best possible equilibrium. For the perfect crystalline solids, they have the lowest entropy and the best equilibrium state. I mean, the lowest energy, right? So now we have a clear picture in mind. Like as we are decreasing the energy, gas to liquid to solid, symmetry is also breaking. What about entropy? Now, see, this is where things get interesting. It might appear to you that as you're decreasing the from gas to liquid to solid, the entropy is also decreasing, and in this case, it is decreasing. Of course, solid has low entropy than gas. But let's talk about the universe. Okay, see, that is why I tell these three very important pairs, and if we can try to find, I mean, we should, if we can find some general means it applies to all systems in the universe, or, I mean, everything, universal relation, correlation between these three players, these three parameters, entropy, energy, and symmetry. I think that can generate very fundamental, important insights into the how the universe works. For instance, the universe began in a very high energy state. That is what our, at least as of now, that is the best explanation we have. That is the Big Bang, very high energy state, Big Bang, and entropy was actually low then. See, this is where I was that's why I was telling that this is where it gets a bit confusing. In the example of gas entropy was high, but gas energy was also high. But in the case of universe, you see, when the universe was just starting, beginning, it was just a Big Bang. It was just a point, very high energy, very high density, but it was just a point. So they were, see, it's just a point. So how many ways you can arrange? You can get that state, just a point. So the number of ways you can get there is very low. But then the universe started to expand. Now, why or how? Then for that I have to go deep into cosmology, inflation theory. Why did the universe started to expand? I mean, the inflation theory basically says that the universe underwent a period of very rapid acceleration just after the Big Bang. Even now, the universe is accelerating and expanding, but at a lower rate than the inflationary phase. I mean, it's actually not always correct to say that the inflation took place after the Big Bang. It's, according to some theories, the inflation caused the Big Bang. But anyway, that's all technical. Basically, what we are trying to what I'm trying to tell you is that as the universe started to expand, see, the volume is increasing and the universe is expanding. And as it is expanding, there were a lot of fields. For instance, the inflation is modeled by the inflaton field. Then, if I just for those of you who are a bit more technically inclined in physics, we have a lot. In the early universe, there were a lot of fields and the particles. There was a particle bath. That is what the term we use, a particle bath. That is basically uh, all the particles. We just think of them as a bath or as a sea of particles, kind of field. They were not at that point of time. They were not yet distinguished like separate particles like fermions and electrons, quarks, everything. Like at that point of time. And then there was a different, like for instance, in some models in cosmology, we say there was a dark matter bath. Like, what is dark matter? It's some we from observations of the galaxies and all, and from due to other observations and other theories as well. We have a prediction. Physicists believe that the universe has a huge percentage of the universe actually dark matter. And why we call them dark matter? Because we cannot detect that matter. It's not, they don't usually interact, and it's not easily detectable. It's not the matter we see around us. That's why we call it dark matter. But we know it's there. We get some indication. But its true nature, what it is, that's what we don't know. There are a lot of candidates, WIMPs, weakly interacting massive particles, etc., and so on. Then dark energy is a different thing. That's not dark matter and dark energy. They're different. Dark energy is something which is which is thought to be responsible for the acceleration of the universe. And then there are a lot of theories, interesting theories like quintessence and this vacuum catastrophe. Like according to quantum mechanics, in vacuum particles can pop up and annihilate. And there is actually a huge mismatch between the theoretical value of the vacuum energy, because vacuum means not zero energy. That was classical idea. In quantum mechanics, even in vacuum, there is a non-zero energy. But yeah, there are a lot of problems. These are all fundamental problems in theoretical physics. So as the universe is expanding, what I was telling you, so the particle bath, and then there was this dark matter bath. So below a certain critical temperature, some particles, then there was some decoupling, and that's why the dark matter, the amount of dark, see, I mean, these are all theoretical models. So let me just talk about dark matter. That was not my idea, not my intention. Let me not talk about dark matter. But yeah, we all use these kind of models like bubbles and all. Then first order phase transition, the electroweak symmetry breaking. We use these models to explain why there is matter in the universe but not antimatter. Because theoretically, we would have expected that whenever matter is created, antimatter is also created. Antimatter is the oppositely charged matter in very rough terms, very non-technical terms. And whenever matter and antimatter collide, they annihilate. Just energy is released, and both of them kind of vanish. But in that case, we see matter around us. But how come this matter exists? Because fundamentally, the universe should have created equal amounts of matter and antimatter, so they should all annihilate and just nullify each other. So there should be no extra matter or no extra antimatter. But we clearly see there is more matter than antimatter. So why this? This is actually what we call baryon asymmetry or baryogenesis. To explain this, there are a lot of theoretical models. Like for instance, what are the conditions that must be met in order for more matter than antimatter? What we call the Shakarov conditions. To understand the Shakarov conditions, you have to understand the CP symmetry violation, CP violation, then a lot of other things, you know. But the point is that, and then to do this, but anyway, point is that as the universe is expanding, entropy is increasing. Why? Because as the universe is expanding, after a certain point, more particles are coming up. The background cosmic microwave background radiation. I mean, there is some decoupling happening, and symmetry is breaking. Why symmetry is breaking? Because it's expected that when just after the Big Bang or at that point of time, the era of grand unified theories also, I guess, all the three gravity is a different thing. There are basically four fundamental forces, and gravity is kind of left out because it's not usually, as of now we have not yet been able to explain gravity in the same way as the other three forces, the quantum field theory approach. But other than gravity, we believe the other three forces, the electromagnetic force, the weak nuclear force, and the strong nuclear force, were unified into one symmetric force, kind of super force. Back then, when the energy was very high and symmetry was also high, symmetry exists at higher energies. Gas is symmetric, gas is high energy. I think you can relate, right? But now, as the universe is expanding, it's also cooling down because, of course, it's expanding, so the temperature is getting distributed and it's cooling down. The Big Bang was a very high energy, high temperature, hot state. Now, as the universe is cooling down, symmetry is also breaking. As the gas is cooling down to water, symmetry breaking, ice symmetry is breaking even more. Same thing with the universe. And this is what we call spontaneous symmetry breaking. So after a certain critical temperature, the strong nuclear force separated from the other two forces, the weak nuclear, and first the three forces were unified, then the strong force separated. This is what we call the electroweak epoch. The electroweak epoch means the electromagnetic and the weak nuclear forces are still unified, but the strong force are separated. Then after the second critical temperature, even the electromagnetic force and the weak nuclear force, they are separated. And today we see all the three forces separately because these three forces are fundamentally different. I mean, at least that's the way it appears to us today. The range of interaction and everything is different for these three forces, right? So spontaneous symmetry breaking, and this explains a lot of things. And the entropy is also increasing because as the universe is expanding in volume, and then the new structures are forming, galaxies, stars, planets. So the number of ways you can arrange all of this in the universe is like exponentially increasing. Is increasing at an alarming rate, and that's why the entropy is also increasing as the universe is expanding. And this is a fundamental law that is the second law of thermodynamics, that the entropy of the universe or of the total system always increases. So you can get that. So it's very interesting to think like entropy, energy, and symmetry. Energy is decreasing. That means because temperature is cooling down, the universe is cooling down, temperature is decreasing. Symmetry is breaking, entropy is increasing. So now if I ask you, if you see even in high school level physics, if you consider, what do systems always want? Physical systems, they always want to reach an equilibrium, stable state. But they, like for instance, glass is not the lowest energy state, so it's not the best equilibrium, but yeah, it has no other choice because we are cooling it down very rapidly. So now if I ask you a question, so that means it appears like everything tries to attain the lowest energy state, right? So the universe tries to minimize energy in some sense. Universe is expanding, cooling down, and energy is decreasing, overall energy is decreasing. But at the same time, if somebody else comes and tells me, no, the universe is trying to maximize entropy, that's also a valid way to look at the situation because we have not observed anything which violates this statement that the entropy of the universe increases. So as the universe is evolving, the overall energy, the overall entropy of the universe is increasing. So that means both of these are true statements. Now the question is, are they equivalent? Like minimizing energy and maximizing entropy, are they always the same thing? I mean, can we think of any system where the entropy is I mean, entropy is. If let me put it in a better way. Does the universe want to minimize energy, and as a consequence entropy is getting maximized, or does the universe wants to maximize entropy and as a consequence energy is getting minimized? I mean, what is the fundamental goal of the universe, purpose of the universe? Is it maximizing entropy or minimizing energy, or are both of these exactly equivalent? If they are exactly equivalent, I mean, in all the cases, if they're the same, then it does. Then yeah, then both the statements are valid. That the universe wants to maximize entropy, the universe wants to minimize energy. But anyway, that's all for the first illustration I wanted to give you, and this was probably the largest one, the longest. It took a lot of time. The next illustrations I will be giving you will probably not take a lot of time. But yeah, I think you get the idea. I'm not trying to answer these questions. Even I don't know the answer. Of course, these are all, some of these questions are how universal are these statements. Of course, we know we know the laws about entropy and energy, and we know we've studied a lot of complex systems and everything. We have some good insights, but yeah, so it's a good question. So I think you can understand, like, the same kind of same driving principles, maximizing entropy, minimizing energy, uh, the same thing, equilibrium, energy, entropy, symmetry, and for instance information is also a very important concept, but I've talked about that a lot I'm not going to do that in this video anymore, I mean now. So if you try to find out the relation between all these parameters, it's a very good that will give you good insights about the universe, and also about, you see, that is what brings me to the next example, which is, I just want to discuss self similarity, or the same pattern getting reflected at different scales. Different scales means it could be length scales, it could be energy scales, but for now let's talk about length scale. For instance, and then I will give you an example about time scales as well. So length scale means, see, we in physics we have some examples. For instance, the same pattern which we can observe in the orbitals of the atom, atomic level, very small length scale. Atomic level means, I guess, what? Say 10 to the power minus 10 to the power minus 10 meters or something. I guess 10 to the minus 15 meters is the nuclear radius, and the atomic radius is probably nuclear, and then you have the electrons. I'm not exactly sure of the number, but it's probably something like that. Atomic level. These are actually called the shape. If you watch the shape of the atomic orbitals when you solve the Schrodinger equation for the hydrogen atom, you observe the similar pattern when you are dealing with Chladni patterns. Chladni patterns means if you're just vibrating some sand particles at the resonant frequency, then you see over a long period, over some period of time, the sand particles will automatically get arrange themselves in that kind of pattern which we observe in the orbitals. But sand particles are compared to atoms, they are very big in size. I don't know the exact, probably millimeters or something, 10 to the minus 3 meters or 10 to the minus 4 meters or something. I don't know exactly, but different orders, different length scales, hugely different length scales actually. So similarly, if you this is why physics is beautiful. If you try to think about this in terms of the emotional fluctuations of a human during his throughout his life, you can see this is an example. The example which I'm going to give you now about these emotions and all, this is not studied, or this is not established scientifically, but let's think about this. For instance, when a human is born, especially during, suppose, let's say, during his school days or the childhood days, okay, just before college, or even before high school, just the primary school and the middle school days, that time he's just he or she is just a baby, just a kid, so immature. Immature means he or she I mean, that person feels very excited, very happy, and very high emotions for small things. If you just give them some toys, they will get very excited, but at the same time if you just scold them, they will get very depressed and they will start crying. The emotional fluctuation over time, the x-axis is the time, over time I'm plotting, and the y-axis is the emotional fluctuation. That means if the above x-axis means positive emotion, so if it goes very high above x-axis, that means that it's very happy, or very, like, kind of very excited, very high. And if it goes way below the x-axis, negative emotion, that means like crying or something, feeling sad or feeling down, feeling depressed or something, I guess. So initially it will be like very up down, it will fluctuate, very, like, it will go very high, then very low, very high, just like a sinusoidal curve. But as the child is growing up with his parents, after some years, and suppose in the school, after some years he will automatically, he will he or she will automatically recognize, like, okay, in school these guys are my true friends, those guys are not my friend, I should not hang around with them. This happens automatically after a few years or few months, I don't know, whatever. It gets stabilized. And once it gets stabilized, you will not, like, for instance, when you just go to school, the first day at school, you don't know anybody, they're just new faces. So if somebody compliments you, you get very happy, and if somebody says something bad, you get very sad. But after 1 year, when you know who are the good guys, who are the bad guys, then if the bad guys tell something bad, you're not affected. I know you are a bad guy, so whatever you tell me, I'm not, you won't feel very sad. Similarly, if the bad guys compliment you, you won't feel very happy, because I know you're a bad guy. You must be doing this for some unscrupulous purposes. So that means after some time, your amplitude of the emotion, it decreases. For instance, initially it was like very high, very low. Then it's still oscillating, because of course life is full of ups and downs, but it's not getting that high and that low. And after a long period of time during a school, like when you're at the end of your primary school or the end of your middle school, when you just before you enter high school, you more or less know everyone. So at that point, it's almost like a straight line. Like your emotion is not very much affected, at least not due to anything at school. So that means now, if you try to think of the pattern, if you try to think of the pattern like this, and like this, like it's a sinusoidal curve with a decreasing amplitude, and ultimately it's almost becoming a straight line. This is this exact same pattern which you observe in a damped oscillation. An oscillator, a simple harmonic oscillator, it's a sinusoidal curve with a constant amplitude, right? Phase diagram is kind of a circle. But if it's a damped oscillation, like damped oscillation means, for instance, the pendulum or any oscillator, it's oscillating, but slowly. So first it's oscillating very fast, and then it's like kind of slowing down, and then it will just come to rest due to friction or due to external damping forces, whatever. So here also similarly, damped for the damped oscillation, if you just plot the damped oscillation curve, it's like this. Same thing here. So that is, say, the first part of your life up to high school, or say up to middle school. Then you go to high school. In high school, again, when you go to high school, initially it's a different, it's a hugely different environment, different kind of people or whatever. Or let's say you go to college, it's a hugely different institution, different faces, different subject, different course, different system. Everything is different. So again, the same pattern will repeat, because initially the first day at college you are again feeling very high or very low. But again, near the end of your college degree, you will again more or less stabilized. But here's the thing, here's the fun thing, the interesting thing. You are older when you're in college than when you're back in high school. So even the first day in school, the your amplitude, and the first day in college, you're still, I mean, you're more mature than when you're in school. So even although it's the first day in college, it's new experience and everything. Since you are more mature, automatically your emotions will of course go high and low, but not as high as it went the first day in school. So again, the same pattern is repeating, but now the entire amplitude is being kind of scaled down. Get the idea? For school, it's like this, and then it goes down. For college, the same pattern, it's like this, and then it goes. But the entire school pattern, the same pattern, but it's been scaled down by a bit. First, it's high, low, then it's settling down. For college, the same thing as well. But the system, it's scaled down a bit. I think you get the idea. Because why? Because you are growing up, you are becoming getting more and more mature. Then in your professional life, the same pattern, but with even less amplitude. Then as you grow old, retirement. But what I'm trying to say is that the same pattern is being repeated at different levels, different time scales. Your time scale, your life, first 20 years, next 40 years, whatever, I don't care. But the same pattern is getting repeated, but it's getting reflected through different time scales, but with a probably constantly decreasing amplitude. I mean, nobody has kind of plotted the emotion versus time, and to plot this, first of all, you need some quantitative measure of emotion. How are you going to measure human emotions, right? So, but this was just to give an idea that the same logic, the same approach of physics applies to life as well, to human. If you look at the behavior of humans, that is to give an idea, of course. But of course, it's difficult to quantify emotions and and actually plot this and see what happens and everything. But let me give you one more example, and that is, you see, in physics, a lot of time we try to keep a system isolated. Like we say, ignore air resistance. But in reality, if you're ignoring air resistance, that means you're considering a system which is isolated. It's not in the atmosphere. The air molecules have no effect on it. And to make the interpretation of our experimental data simple, in labs, oftentimes we try to work with the isolated system. Isolated means we try to say create a vacuum in lab or something, because otherwise you're trying to study some aspect of the system, but if you don't isolate it, then the air molecules are also, that will have some different effects. So when you get the results of an experiment, you will not understand whether the results or the fluctuations in the data due to the air molecules or due to what you're actually trying to study. So it's always good idea to isolate it. But if you try to apply this logic to your life, see, that's what I say, it's always sometimes important to, people will say like it's your life, so you should always be in control. That's what people say, like you should be the one who is driving the car, you should be behind the wheel, you should not be at the back seat. But I think sometimes it's important to be at the back seat, because what I mean is that okay, let me just instead of using the word back seat, I mean sometimes it's important to be the referee and not the player. Like we are all players in this game of life. For instance, it's a football game and something all the players are playing. But when Cristiano Ronaldo or Lionel Messi is playing the game of football, or when any good player is, any good footballer is playing, he or she, I mean that player, what the player thinks, the player only thinks about scoring a goal or preventing the opponent from scoring, and he only thinks about my team members. Okay, I have to pass the ball to that team member because he is a pretty good striker, or maybe he will pass it to that is, I mean it's very limited. He a player who is playing the game, when he's playing the game, he does not think about the entire game, the entire field, everything. He just thinks about his own team, how he will score a goal, or how he will, or in case he's a defender, how he will prevent the opponent from scoring. So if you're, of course, in the game of life, you are the player, you are a player, you are an active player, you are playing your game. I am playing my game. We are all players in the game of life. But sometimes it's important to stop thinking about yourself as a player, because if you always think that I'm the player, I have to play the game, then you will only think about that. But now think of the referee. The referee is not playing himself, but the referee is the only one who has the entire view of the field. The referee has the entire view of the field of both the teams, how the players are playing, how, the entire view, overview of the game. For instance, the drone's eye, what's sometimes called the bird's eye view. The referee is actually analyzing each and every player, not just of his team, but of both the teams. And if you are a referee, because a referee doesn't have to worry about scoring a goal himself or preventing a goal himself. So that means he is free to think about the entire game and analyze the patterns, understand the patterns of the game. But if you are thinking of yourself in terms of player, that means you are not, that means you are too occupied with playing. You cannot spot the patterns, the bigger patterns. Same thing, that means referee means he is isolated system. He is not part of the game, he is just watching the game. But a player is not isolated system. The player means he is interacting with other players, he is actually playing the game. So that means, see, whenever you isolate a system, that means whenever you become a referee from a player, you analyzing the entire game becomes easier. The same thing in physics. Whenever you isolate a system, studying experimenting on it or studying it becomes easier. So if you think about it, there's a lot of analogies. One more thing I want to mention in this video is that, you see, a lot of people like see, let me put it this way. A lot of people ask me, not just me, a lot of people are wonder like physics is generally perceived as one of the most difficult subjects out there, and of course no doubt it is difficult, but I think this has a lot to do with a lot of people ask me like for instance some juniors also, can I become a physicist? I really like physics, or at least I want to try out physics, but can I really become a physicist? Can I really become a scientist? See, becoming a physicist, becoming a scientist takes a lot of training, lot of professional, I mean lot of formal training, advanced training. It's not easy, of course it's not easy, but see, that all depends on let me just if I just try to give an example. In physics, for instance, just a simple high school level example, kinetic energy and potential energy. The sum of this kinetic energy and potential energy, that is the total mechanical energy of a system, must remain constant at all points of time. So for instance, if you are sitting at the top, then your potential energy is maximum, but you are at rest, you are not moving, so the kinetic energy is zero. Suppose a ball or something, suppose an object, I have put it at the top of a tower, its potential energy is maximum, kinetic energy is zero. Then I push it and it starts falling. Now as it is falling, it's accelerating, its speed is increasing, I mean its velocity is increasing, so its kinetic energy is also increasing. And as a result, its potential energy is decreasing, because the sum of the kinetic energy and the potential energy must remain constant. If you look at the formula, you can get potential energy is proportional to the height. So as the height is decreasing, the potential energy must also decrease. and when it touches the ground, just before it touches the ground, its velocity is maximum, kinetic energy is maximum, and at that point the height is almost zero, so the potential energy is almost zero minimum. Get the idea? So similarly in life, I think not just about physicists or scientists. In life, a lot of people, they what they do is that they have a lot of potential in them, they have a lot of potential energy, but they are too afraid to start, they are too afraid to take the first step. Can I really become a physicist? I'm not sure, it's a very difficult subject, let me just maybe choose something else, or I don't know. So they're always in a state of indecision, like am I really taking the correct decision, let me just. But if you have a lot of potential energy, but if you're not converting it into kinetic energy, if you're not doing something, if you're not making any progress, then that is just waste of your potential. Because suppose I keep the object at the top of the tower, nothing is going to happen. Something is going to happen only if I push the object, only if I convert the potential to kinetic energy, then the object is going to fall in the ground, maybe the ground is going to, or if it falls on someone's head, then that person is going to die or something. I mean, whatever, something is going to happen. But for something to happen, the potential energy must be converted to kinetic energy, at least partly. So what physics teaches us is that always it's not always possible to determine whether this decision which I'm taking now, whether this will be a good right decision or wrong decision. But just do something. I mean always, I mean never choose not to act, always do something. You feel like this is your right path, you feel like you find this interesting, just do it. If at a later stage you find this difficult, then fight and try your best to establish yourself, or otherwise then you shift some. I mean, see, learning can never be a waste of time, even if you don't pursue that as your profession. So that's what I'm saying. It's not always possible to determine whether this decision is a good or bad decision, but that doesn't mean you'll just do nothing and sit quietly. That's something that physics teaches us as well. Because see, a lot of people are like, also for instance, in my experience also, they're like, should I do this? What he or she will think? What maybe my relation with that person will get affected if I do this. See, ultimately you will be remembered for your work, not for your relations. That is the most important realization that a human can have. You will nobody's going to remember you for your relation with that person or your relation with that person, this person. There, but you will be remembered for something objective. Today you are on good terms with this particular person, but there is no guarantee that tomorrow he or she will not stop talking to you or block you. So that is not objective, that depends on that person. But now if you publish a very good paper in physics, or if you get a patent, or if you get a Nobel Prize in physics, or if you whatever, if you just release a song which becomes a billboard hit or something, these are your works. Nobody can take this from you. Your relation with some other person, that other person can take it from you. But this kind of success, suppose you found a company, you become the founder of a company, nobody can take these things from you. So you will be remembered for your works, not for your relationships. That is also something important, and physics teaches us this objective, and also this kinetic to potential energy stuff. That's also a very good important, I find as a good important. See, problems in life, I mean life is, I mean, see, if you order something in Amazon, you check all the specifications, this is what I want, you check all the reviews, and then you order something on Amazon consciously, and then the product comes in a very good state. But suppose after using it you find that no, this is not the product I wanted, this is not suiting my purposes. So if there can be problems with something you consciously order after seeing all the specifications, then this life is also a product, kind of a product. And of course you have not placed an order for your life, but say you were not given the chance to choose the specifications before you were born. You are not given the chance to choose your name, your place of birth, your whatever. You could not choose the specifications. So if even after choosing the specifications and ordering something from Amazon, if there can be problems, then it's obvious that there will be problems in life, because nobody of us chose this life, chose this existence. We are just kind of lost in this world without a clue. So it's expected, it's obvious there will be problems. But so yeah, but does that mean that there is no way to deal with these problems? No, of course there are ways to deal with these problems, actually even physics can teach you a lot about this. So that's very important. Two more things I would like to, two more kind of illustrations or examples I would like to talk about before finishing this video. One is that, see, in physics a lot of times we model the behavior of systems using differential equations. Very important tool, differential equations. But a differential equation is actually mathematics. If you solve a differential equation, you get a general solution. For those of you who are not aware of the technicalities, what do I mean by general solution is that, Solution of a differential equation is general in the sense it's just a solution. I mean, for instance, you get a solution like a cos theta plus b sin theta, something like that. That's it, but you don't know the value of a and b. All you know that there is a constraint that a and b must be constant. That is the only constraint. That is the only like only condition on a and b that you have imposed. But there could be any constant. I mean, just from the general solution, you cannot uniquely determine the value of a and b. But to determine that, you need some boundary condition. For instance, mathematicians will just solve differential equations just to study the mathematics. But physicists will just, I mean, physicists will only solve differential equations that can model a physical system. So suppose you're studying, let's say you have a string attached with this in this wall, and you're studying this. It's vibrating, and you're studying the wave equation of a string. That's the wave equation is also a differential equation. So then boundary condition means since the string is attached at this end to this wall, let's say this corresponds to x equal to 0. We have defined the origin here. Then the amplitude of the string of the wave at this point at x equal to 0 is always 0. That is a boundary condition. I mean, this is always true because that is how the system is defined, physical system is defined. So if you put in the condition that the amplitude is 0 when x equal to 0, then that is a boundary condition. So if you put in the condition, then you simplify the general solution and you can get the value of these constants a and b. Just an example, okay, not any specific example. Then there is something called initial conditions. If you know the initial conditions, that means suppose you are studying the system starting from time t equal to t0, t naught, or say time t equal to 0. We define the time t equal to 0 for simplicity. That means when you're just starting the study of, suppose you want to study the evolution of a system. Now when you're just starting, you know the state of the system when you're just starting point. So those are your initial conditions. You know that, and then using the equation you will try to model what happens to the system. Hence, from this point in time, like after this time, what happens to the system as the system evolves. So to answer that question, you solve the differential equation, you get a general solution. But since you know the initial conditions, using the initial conditions, you can determine the value of unknown constants and get the exact solution. Suppose a cos theta is the solution. The value of a for my system is, suppose, let's say 3. So 3 cos theta is a particular solution for that system. It's not a general solution. But a cos theta is a general solution when a can be any constant. So now illustration, like how can we relate this to life? Very important aspect of human being, a very important skill, I would say, is actually a skill, is temper control, temper management, managing your temper. Because see, I know today's world is very hectic, very stressful, and a lot of people lose their temper. Even I do in my home sometimes. But I try my best. I mean, now I don't do that in college or in my whenever suppose I'm in an online meeting with somebody who is like, for instance, I try not to do it in my professional life, professional environment. And even at home, I try not to do it. But yeah, sometimes it happens when I'm in my home with my parents. I mean, with the people I'm comfortable with. That's my parents. Then it happens. But see, because if you lose your temper, if you lose your cool in a professional setting, then that gives the impression that you are someone who is not in control of your own life. So how can you be in control of your team in the professional setting, right? So, but there are a lot of ways to manage your temper. But I think, at least personally, those are just, yeah, they don't work, especially. I mean, and it's not possible for someone who has a lot of work to do. It's not possible to meditate daily for 30 minutes and do all of this psychological exercise and all. But there is actually a pretty simple way to control your temper, and this is very simple. You don't need to practice this for 5 minutes daily. Not that kind of a solution. It's a very good solution. I'm not sure if this will work for you, but this works for me at least. That's why I want to tell you, and that's why you can understand the link with physics. I mean, not with I mean with what I discussed about the differential equations and boundary conditions and all the that part. Whenever you suppose whenever somebody around you in your profession, in your college or in your office or in your workplace or even at home, if somebody makes some comments which or somebody tells you something and you are like you can inwardly understand that, okay, I'm getting angry, I don't like this, maybe there will be an outburst. You just keep telling yourself mentally, inwardly, keep telling yourself that this person is doing this to anger me. I mean, this might not sound like any like out any rocket science or anything, but just try this. It actually works wonder. It is for me. Whenever you're getting angry due to the action or if somebody says something and anything, Just you just keep telling yourself and keep convincing yourself mentally that he or she is doing this intentionally to make me angry. That may not be true. Maybe that person is not doing that intentionally to make you angry. Maybe that person is genuinely whatever, genuinely just saying that that is what he or she feels. It could be the case. But if you convince yourself, then automatically you will not get angry, or at least not on the outside automatically, because then what you're see, if you don't think this way, then you are like, okay, you are saying this, I'm very angry, and there will be outburst. But if you convince yourself that that person is intentionally doing this to make me angry, then you are like, okay, if I don't get angry, then actually I win the game. That person will be irritated and frustrated. So let me just enjoy the game. I'll not get angry. Just tell whatever you want, whatever the hell you want. I will not get angry. That kind of attitude. So it's pretty simple. But so see, this is basically the wrong initial conditions. Suppose initial condition means what? If you or the inputs of the theory, input, initial condition, whatever you say, or the if you tell yourself that that person is doing this to anger me, to make me angry, automatically your behavior changes. You are no longer feeling angry. But if you tell yourself like that person, if you don't tell yourself this, if you don't specify this condition, like I'm just kind of trying to compare this with the initial conditions, then you have a general solution. Then most likely you will get angry, and you can be there can be different outbursts like a general solution. But to specify that condition, that when your constant will be 0, that means suppose you have some constant into anger. So if you can make the constant 0, that then 0 into something is 0. So you can like eliminate the anger. So that means you will not get angry. But to do that, you need some specific external conditions. I mean specific input condition. That means you have to give some input to your brain, and you have to feed this thought, this idea, or this belief to your brain that he or she is doing this intentionally to make me angry. Even if it may not be true, that is what you have to do. It's a good analogy, right? And the last point I want to discuss in this video is that about the relation between physics and math. Very, very interesting and very important as well. You see, mathematics, a lot of people will say that mathematics is a tool which is used by physics, and that's true. But let me try to give a very interesting example about this. Why do we use mathematics and physics? Because if physics started as a study of the world around us, so it was not like initially people didn't have any obvious reason to use mathematics and physics. But why is the way it developed? Because number one, mathematics is objective, and oftentimes it simplifies things. Usually high school students will say that maths is very difficult. It does not simplify. It complicates my life. It does not simplify things. But actually, let me give a simple example. I mean, this example will probably, you will not be able to appreciate this example if you don't know electromagnetic theory. And electromagnetic theory is probably not a very, I mean, it's a pretty advanced topic. It's probably taught in the physics undergraduate courses. But yeah, still try to, I mean, some of these ideas you should have even in high school as well. Yeah, if you study physics, if you have studied physics at your high school level, higher secondary level. So I'll just try to give you an idea. Suppose electromagnetism means, suppose first of all when we study electricity and magnetism, first thing we study is Coulomb's law. Basically, the two charged particles will attract each other if they are unlike charged, like positive charges attract negative charges, and if they're like charge they will repel, and all of these things. So basically, Coulomb's force. First of all, we study force. Like this charged particle can exert a force on another charged particle, and this is the physics picture, because whenever we're trying to think about in terms of force, we can visualize, okay, this particle exerting force is physics at this point. But you see, if you try to calculate the force between two charged particles according to Coulomb's law, if you don't know the mathematics, that's not required to appreciate this example. Okay, but yeah, just to give an idea, Coulomb's law is it's some constant. The force that a particle with charge q1 exerts on a particle of charge q2 is given by some constant k multiplied by q1 into q2, that the product of these two charges, divided by r square, where r is the distance between these two charges. So to calculate this force, you have to know q1, that is this charge, the source charge, which we technically call. You have to know q2, the test charge. Test charge means the charge on which the force is being applied, the force by the source charge. And you also have to know the distance r between them. So you have to know q1, you have to know q2, you have to know r. So three things you have to know. That means you have to have a lot of information. That means although force is very physics in a way that you can visualize and everything, but the force description, to work with the force description, you need to know a lot of information. It's not always possible in reality, especially for more complex scenarios when you have a lot of charges and charge distribution. For instance, it's not always just a single two charges, right? In reality, when you're studying electrostatics and charge distributions, there are a lot of charges, continuous charge distribution, volume charge distribution, currents, and more complicated scenario, right? So next is that let us move to the field formulation. Now then, as we study more electrostatics and electromagnetism, there we are introduced to electric field and magnetic field. So what is the electric field? So electric field is nothing physical. I mean, force means we can actually visualize the physical particles. They are exerting force. They are attracting each other or they are repelling each other. But when I say electric field, nothing comes to your mind because electric field is nothing that can be visualized or that can be seen or that can be felt. It's just a mathematical construct. We have defined the electric field to be the electric force per unit charge. Uh, F is QE, so E is F divided by Q. Or mathematically, if you look at the formula, the basic formula of electric field, it is KQ1 Q2 by, it's KQ1 by R square. KQ by R square rather. Just force was KQ1 Q2 by R square. Just remove one charge. Just remove the electric field. See, when we're talking about the electric field, we don't consider the test charge. We only calculate the field due to the source charge. Suppose there is a charge Q1 sitting here, so the field due to that charge will be KQ1 by R square. R is what? The field at a point R. That is what we're calculating. The electric field at a point R due to a charge Q1 will be Q1 by R square into some constant K. K is usually that 1 by 4 pi epsilon naught, but let's not go into the technicalities. If you don't know what K is, not required. That's okay. That's just a constant. Okay. But see, what is the beauty of the field description is that now to calculate the electric field for a charge, you only need to know that charge and the distance, the point at which you're trying to calculate the field, the distance of that point from that charge. You don't need to know the test charge or anything. So you are kind of reducing the number of parameters, number of inputs to the theory, right? Now you can say that, but if I want to suppose I calculate the electric field, see why is this why this makes our job so much easier is that because for a single charge it's okay, you can directly calculate the force. But say you have a charge distribution, suppose 10,000 charges in a particular distribution, and you just want to calculate the force of this entire distribution on a single charge that distance away. So of course you cannot for each charge you have to know the charge. You have to see, you are doing the same thing over and over again. For this charge you have to for this charge the force on that charge is this way. Force is a vector. Then for this charge the force on my test charge is this way. So for 10,000 charges you do this individually force and then you can find the resultant force. Very difficult job. That's actually impossible to do in practice. But otherwise, if you use the field formulation, you just find the electric field for all these charges at once, because the law of superposition, you can just do that. And then due to this with this electric field, you just multiply the test charge, you will get the force. Right? Ultimately, to get to the force, you still need to know the test charge, but the field formulation makes your job a lot easier. But here's the thing, see, you're moving from physics to mathematics because field is more mathematics. There is nothing to visualize. Now we will go one step further. Potential. Electrostatic potential, V. See, it's again, electrostatic potential is not something you can visualize. What is potential? It's just something we define mathematically. Electric field is an irrotational field. The curl of electric field, that is curl of E is 0. What is curl? That is actually, we write it like this. It's a cross product of this Nabla operator with the electric. Those are all mathematics, but you don't need to know all of that. And it's not possible for me to explain what curl, gradient, divergence, and everything vector calculus in a few minutes, right? So I'm not going to even try. But basically, mathematics tells you that if the curl of a field is 0, vector field, that is the electric field in this case, if the curl is 0, that means the field is irrotational. Then you can write that field as the gradient of a scalar potential. So that is why mathematics tells me that I can write the electric field E as minus grad V. That's a mathematical formula. You don't need to know what grad is. Grad is basically a kind of space derivative, but you don't need to know all of that. But mathematics tells me that I can define a scalar potential V, and if I know V, then I can calculate E, electric field E, because E is just minus grad V. Or I can calculate E, and if I know E, then I can calculate force. So force to field to potential. But say potential, it's just a mathematical concept. How to find out the velocity? The V, the potential. For that you have Poisson's equation. That is the grad square V, that is the double derivative of V is equal to, I guess it was rho by epsilon naught. Rho is the volume charge density. And all of these, then basically this is a differential equation basically. And if you solve it, if you know the initial conditions, boundary conditions, you can solve for V, and if you know V, you can know E. That is the way we do electrostatics, but that is not what I'm trying to tell you in this video. See, That was about electricity. Now magnetism, in magnetism also is the same thing. We define an abstract mathematical quantity called the magnetic vector potential, called A. That is a vector quantity. The V in electrostatic, that is a scalar potential V. But A in magnetostatics, in magnetism, A is a vector potential. So why we define A? The reason is pretty like, in case of magnetism, we know that the divergence of B, that is the divergence of magnetic field, is zero. And again, mathematics tells me that if the divergence of a vector field is zero, then I can write that vector field as the curl of another vector field. So we write B as curl of A. We just define an abstract vector potential A. This A has no physical kind of visual. Magnetic field you can at least visualize to some extent. If I have a lot of iron fillings and I just put a magnet, they will be arranged in the field lines and all these things, north pole to south pole. But magnetic vector potential, you cannot visualize it physically. There is no physical kind of analog to the just a mathematical vector potential. But why do we do this? Because now it's not possible for me to technically show you derive Maxwell's equations and everything in this video. But basically you can write the magnetic field B as curl of A, and you can write using this and using the Maxwell's equations, which are the equations governing this electromagnetic force. From Maxwell's equation, using Maxwell's equation, you can also write the electric field E as I guess it was minus grad V. This V is the scalar potential. Minus grad V is also, we already know from electrostatics, and then minus, I guess it was a term containing this magnetic vector potential A. Because that was for the electrostatic case, minus grad V. Then there was no concept of magnetic vector potential, because electrostatic means the charges are at rest. And if the charges are at rest, then there is no magnetic field or anything. Magnetism does not come into play. But for the most general case, electromagnetism, when the charge is moving, then there will be both electric and magnetic fields. Then you can write the electric field in terms of both A, the magnetic vector potential A, and the electrostatic scalar potential V. And the magnetic field is just in terms of A, curl of A. So if you know A, you can find B, and if you know A and in addition if you know V, then you can find E. So suppose if I tell you to find the electric field and the magnetic field directly, so you need 6 components, because both the electric field is a vector and the magnetic field is also a vector. And a vector has 3 components in 3 dimensions I'm talking about. So you need 6 components to find out electric field and magnetic field. But on the other hand, if you find out V, the electrostatic scalar potential, that is just a scalar, so just a single component. And if you find out A, the magnetic vector potential, it's a vector, so it has 3 components. Okay. But now if you find out V and A, in total you need to find out 4 components, the 3 components for the vector A and just the scalar V. But if you know these 4 components, then you can just using the mathematical operations, taking grad or curl and everything, you can find out E and B. So basically you have reduced the problem of finding 6 components to finding 4 components. But physically it's the same thing. The physics is not changing. If you find out A and V and use it to find B and E, is the same B and E, same magnetic field and electric field. The physics is not changing. But the more we are moving towards mathematics, actually our job is getting easier. That is why physicists use mathematics. Physicists always try to, that is the approach we do physics. Be it astrophysicists trying to find some, Bayesian inference in astrophysics, cosmology, trying to constrain some cosmological parameters, or be it some particle physicists who are trying to reduce the number of arbitrary parameters in the standard model of particle physics, whatever it is. The basic philosophy, the basic approach in physics research, in much of physics research, is that we try to find the similarity between 2 different phenomena and try to reduce the number of inputs we need to calculate our answers. Reduce the number of fundamental inputs in the theory, or at least we try to show that maybe this parameter is actually symmetric to that, so that means they are actually the same thing. I mean suppose apparently it appears that parameter A and parameter B are different, we need to calculate separately. But then suppose if some physicists can show that they are actually symmetric, that means if I know parameter B, I can actually find out parameter A from that knowledge without having to calculate it separately. Or maybe if I can show that they are equivalent, or maybe if I can show that they are not independent. Suppose initially it appears that parameter B is, suppose we have 2 parameters X and Y, and initially it appears that they are independent. Independent meaning I have to separately find out X, I have to separately find out Y, otherwise I will not have the full theory. But suppose if somebody can show you that Y is actually 5x minus 2, suppose, just an example. So then suppose you find out X, then you don't have to separately find out Y. You just multiply X with 5x, then subtract 2, 5x minus 2, you get Y. X and Y are not independent. So that is what we try to do. We either try to show that these some things are not independent, they are related, and using by exploiting the symmetry of the relation, we try to reduce the number of fundamental inputs we need in a theory. And basically in simple words, we try to make our job more simple using mathematics. Yeah, as a consequence, yeah, we have moved to more abstract mathematical description. For instance, when you're talking about force, it's easy to visualize. Then field, not so easy to visualize. Then more mathematical formulation, say vector potential. Or this was just an example of electrostatics, of electromagnetic theory. But even in modern physics, see, the more we try, it has become more and more abstract, more and more mathematical. As I've discussed this in a lot of my previous videos. So that was all I wanted to discuss in this video. And basically, guys, the idea of this video, again, maybe I didn't talk about in a very organized way about any specific topic, but I just want to give some idea that physics is everywhere around us. There is a very famous quote, like, everything happens for a reason. The reason is usually physics. But I say that everything happens for a reason. The reason is always physics. Maybe we are not able to understand the physics behind everything, but there is physics behind everything. It's always physics. So I just wanted to illustrate some examples from real life and physics, just to maybe my idea was to uh, establish that physics is very physics. If you think about it in a right way, physics can be very interesting and even enjoyable. And of course, it's difficult subject, but yeah, I mean, how not to hate physics part two. We should not hate on it. And it's not like physics means something to hate, something very difficult, something which is detached from the physical world, detached from the real world of humans. It's just mathematics. No, it's actually everywhere around you. If you look at the behaviors of humans, look at the behavior of systems, it's just physics. It's not detached. It's everywhere around you. So yeah, I guess that's all for this video, guys. And it's already a pretty long video, so I think I'll stop here. Thank you. Thanks for watching.